story, I suppose, before I launch into the presentation, as it were. I moved here to Bergen 2.5 years ago, and just before I moved, I had a call with my now colleagues about the project I'd start with. And the first thing they said was, "You're going to come to Norway and you're going to the mountains to measure the snow." Fantastic. It couldn't be any more of a Norwegian start to bring me into this kind of project and this kind of world. Coming to the mountains to measure snow here. But what I suppose I didn't realize at the time was just how important the snow is to Norway, I guess. So snow effectively powers the hydropower system that we have here in Norway. So here is beautiful snowy landscape up in Mjøkdalen near Bergen. But actually, the snow itself stores up a huge amount of energy, effectively, that we use as hydropower. Norwegian hydropower produced 137 terawatt hours in 2023, and that's 89% of the total energy mix came from hydropower. But of that hydropower, it all comes down as precipitation is part of the water cycle, and 1/3 of the precipitation fell as snow. So snow is actually hugely important for our hydropower reserves. It's kind of like the battery that Norway builds up through the winter to power us through the rest of the year. But there's huge unknowns in the amount of snow that we have. So this plot shows effectively the snow levels over a year and the amount of energy stored in the snow. Each color on the graph is a different year for the past 30 years, I think. And you can see the variation year on year in the energy stored in that snow is enormous. Some years we have 2, 3, 4 times as much energy stored in the snowpack as we do in other years. So we really need to know about how much energy we have in reserve to control our hydropower works. But to find out about how much snow we have and how much water is stored in that snow, we have to make measurements of the snow. And in the past, these have always been manual. So we send people up into the mountains, they need to navigate their way across a basin filled with snow, dig out a core of snow and measure the water contained inside. So this is a very manual process, it's very costly, it's not without risk to go to these remote places. And that was the only way that people had to measure what we call snow water equivalent. That's our most important parameter, I suppose, for the hydropower market, knowing what's the water equivalent of the snow that's stored up there in the mountains that we can use for our power generation. Knowledge of that snow is really crucial, and to put some kind of numerical and financial number on the amount of on the information, the value of the information, we've got this independent research here. Wasn't produced by us, paper that I found, and somebody did a lot of simulations of the value of information on the snow for the scheduling of hydropower production. And just going from a scenario with no information about the snow at all to a scenario where they made regular measurements at a certain location, they increased that energy production value by 10% over a whole year. And to put that into financial terms, remember the 137 terawatt hours that was produced from hydropower in 2023? It's approximately 0.7 kroner per kilowatt hour on average in 2023. So that's a 99 billion kroner total market here in hydropower, the value of the energy produced. So even if we can just make a 1, 2, 3% gain in efficiency and the way that we can use that power, we're talking billions of kroner here very easily. And hopefully our system can do several percent. So we could easily have quite a large effect on the market by giving better snow water equivalent information. So what happens with snow water equivalent today, I suppose? It is possible to use not only manual measurements of doing these things, but it's possible to use satellites and autonomous drones. They can take images, they can use radar-based systems, but they always need in situ ground measurements, some kind of ground truth of what the actual snow is on the ground. It's very easy to take a picture of the Earth from above and say, oh yeah, snow, no snow. But what we don't know is the density of that snow often. So we don't actually know how much water is in a snow-filled area. The only way we can get that information is having these in situ ground truth measurements, but they're taken infrequently if they're manual, or even automated stations are just single individual points, when actually the basin size for a hydropower catchment can be enormous. So our project, the Messenger SWE project, proposes to have much larger scale snow water equivalent monitoring comparable with the sizes of pixels that we can measure with satellites. Therefore, we can give a much better and much more accurate figure, a ground truth of the snow water equivalent measurement, which we can feed into a model used over a wider area by a satellite. So this can give us better area coverage of the ground truth measurement itself, and can give us much better coverage when we scale up our models over a wider area. There are already some methods of making these in situ SWE measurements today. Here is an example from up in Myrkdalen, near Bergen here. And this is a set of snow scales. So the platform in the center there is 5 meters by 5 meters, and it's simply a set of weighing scales. The mass of the snow can very easily tell you the mass of the water held within it. So it's the simplest way, I suppose, of measuring the snow water equivalent. And there's other instruments available. There's snow pillows. So instead of a huge wooden platform, you have a sort of a bag filled with liquid, and you measure the pressure of that bag, again caused by weight. There's gamma ray instruments, and there's a few other techniques on the market for these automated snow water equivalent measurements. But as far as we know, especially from talking to our colleagues at NBE who are advising us in this project, this is kind of the gold standard, is having a massive set of scales to measure the weight of the water, because it's very hard to dispute the water equivalent of when you know its mass. But to build something like this, something this enormous, it takes preparation. And underneath this set of scales, there's been dug out a huge drainage channel. It's been filled in with gravel. There's had to be power infrastructure put into place. There's had to be all kinds of digging out and construction and groundwork to put this sensor here. This particular location, we're lucky. We can drive there on a track in the summer months. But imagine doing this in some remote mountainous area that's really hard to get to. It's a huge amount of work and infrastructure that we would need to put in just to make a single point measurement of snow water equivalent. When all of this is in place, we can only measure the snow water equivalent that we're measuring the weight of at this particular moment. We can't say anything about the wider basin around us. So it's a huge amount of work just for a single point measurement. So this is where the Messenger optical fiber sensing mat design comes into play. The idea is to have a mat, and on top of the mat, snaking around, we have an optical fiber cable. And then the load, which is the snow falling on top of that mat, causes the light transmission through the optical fiber to vary. So when there is a high load pushing down on our fiber mat, we have quite a lot of loss of the optical signal. When there's not so much load, there's not very much loss of optical signal. So the variation of the optical signal through our sensor mat from the mass of the snow on top of the mat can tell us a lot about, well, can tell us exactly the weight of the snow on top. So if we build up our sensor from scratch. We start with a rubber base sensor. In last year's design, there was just a rubber mat on the floor. On top of that, we have a special structure of rubber impactors, we call them, because these are specially designed and characterized pieces of rubber which impact upon the optical fibers immediately above. And everything is designed carefully to give just the right amount of optical loss that we can measure at the appropriate scale for the mass of snow that we expect. So we have rubber base, an impactor layer, optical fibers layers, another layer of fibre on top to protect the optical fibre, and it's on top of this that our snow falls. It causes deformation of the optical fibre, and that's what gives us the optical signal loss, which gives us the weight measurement. Relatively simple components, but a large engineering challenge, I suppose, to exactly select how to combine everything together and which components we need of which size and which material. We can scale these mats to tens of meters or even hundreds of meters, and that's what enables us to make these measurements over a much wider area than just a single point measurement with the scales as we've seen before. So here is what it looks like in practice. Here are the samples we've made in the lab. Each of these mats is approximately 0.7 meters squared, and we can put 6 of them together to get a 2 by 2 meter box. And inside we have 2 independent optical fiber loops, and that gives us redundancy, so that if one optical fiber should break or it should be eaten by an animal in the summer, for example, we have another fiber loop in place that's going to keep our sensor active. But it also means we can have different sensitivities. We can have one fiber that's very sensitive, so very good for smaller amounts of snow, one fiber that's less sensitive and can cope all the way up to meters and meters of snow depth at the end of winter. So it gives us a much better measurement range as well. Here's what it looks like in practice. So this was installation of last year's design. We could just lay the sensor mats out straight on the ground. So compared to what we had with the scales, where we needed to go and dig in depth and take a big machine out to excavate and put in the drainage channels and put the load cells for the scales, dig them down, cement them in, there was none of that. We could walk up to our measurement site, place our mats upon the ground, maybe cut down the grass a little bit underneath, but then we're done. We're talking a day to install several of these mats rather than a hugely planned and maybe a week's worth of groundwork. There's minimum work required to install these sensors, which makes it possible to install many more of them over a larger area. This is where NVE, our project partners here, already measure snow water equivalent across Norway. So every single one of these sites, NVE has some equipment, often scales, perhaps just snow pillows, to measure the snow water equivalent. So we chose 2 NVE stations that were relatively close to Bergen, one up in Myrkdalen near the ski resort, sort of tucked away inside the ski resort, and one in Filefjell, Kjøkstølandet, which is on the border between Westland County and Inland County. So quite near to Bergen. And we installed these messenger sensors for last winter. We did a very little pre-project before that even, but we did a full-scale installation of 10 different sensors last year, and we've repeated that process again this year. We can see what happened when we started to install the sensors here. This is a time-lapse video of installation. You can see some of our sensors on top of the scales here, so we can directly compare our results with what NVE measured with the scales, and other sensors that are directly on the floor. And did you see there? Overnight, we went from bare ground to sudden snow cover. But what's quite nice to see is the presence of the mats didn't really affect the snow coverage. It doesn't seem to have caused an enormous lump. The mats themselves aren't covered differently to the surrounding ground. The mats have had very little impact on the snow coverage. But compare that to the scales that we can see on the right here, that kind of thick layer of scales where the wooden platform and the load cells cause the scales to be loaded up. It's taken about 3 weeks in this time lapse for the snow to reach the same level, kind of a constant surface across the scales, as in the rest of the area, which is very different to our thin layer of sensors, which caused a natural response within just a few days. So let's look at the actual data we got back from the sensors. Was it comparable? And here is the measurements that we made from the messenger sensor compared to the NVE snow scales from our samples, where there's the arrow in the image on the bottom right here. So on the graph, the left axis and the blue points are the NVE snow scale results, and the orange sort of color is the messenger sensor results for the right hand y-axis. And there's quite good agreement, but there does seem to be some sort of time delay effect. As we look across the x-axis in time, the snow scales did seem to respond more quickly than the messenger sensor. And we have a couple of hypotheses for this. The first is that there is some sort of time delay effect because it's the natural elastic deformation of the rubber. So that's kind of an inherent part of our sensor, is it will take time for the rubber to deform and bend the fibre and cause the optical locks. The second is the way that the snow forms. Snowpacks generally build up in different layers, and so the gradual sort of compression of that bottom layer into the rubber matte surface can give us an interesting settling effect that takes some time. And the third thing is that there's the sensors we know have a non-linear response. It's a repeatable and characterized response, but we wouldn't expect to see a non-linear response to snow. So the time delay may not be as bad as we think. It's just sort of exaggerated when we see it on a linear axis, but we know the optical sensor response is non-linear. But with that said, broadly speaking, we're quite happy with these results, quite satisfied that our messenger sensors can give a broadly equivalent response to the existing state of the art so far. As well as not needing huge amounts of groundwork, we can think about the rest of the infrastructure we require. So the scales and the other measurement equipment required permanent power and permanent data connectivity. And we were very lucky that all of these towers are in place at the meteorological site. So we can attach our sensors up alongside the existing infrastructure. But we can also place the electronics part of the system. So we have our optical fiber sensing mat, which is the big mat that experiences the optical loss. We have an electronics box that contains the laser, the detector, and some mobile phone connectivity to send the data back to us. We could just place that on the floor. We included one sensor where we tried, instead of putting the electronics up on a mast, we left it on the floor next to the mats. And it worked just as well. It could take hourly measurements and send them back to us over the mobile network 4 times a day for an entire winter, just on normal battery power. And there was no problem using the mobile network while it was under 2 meters of snow at the very peak. So I think we can confidently say we don't need expensive and challenging groundwork of any sort, not just to clear the ground, but not even to mount towers or to bring in power supplies. Our sensors could be put absolutely anywhere. We can also put the sensors out on some sort of hilly and sloping ground, so we're not limited to just somewhere that's totally flat. Here are another set of sensor mats, the same design last year, but they were placed out on the slope. What we do see here is that there was a little peak measured by the snow scales in the first heavy snowfall in around the 15th of December here, but then it recovered. And then there was good agreement again after that. And partly that could be down to the challenges of having the mats installed on the slope. we may need some kind of in situ calibration where we calibrate the sensor's response in the particular position that it's installed. So here it's installed on sloping ground, and we just need to apply some weight, measure the response, remove the weight again as part of the installation process. And that is a topic that we're probably working with most actively in the project now to perfect for the kind of finished product when the project concludes. We were told by our colleagues at NVE that size matters when it comes to building snow scales. The most important thing they had for us was that all of your sensors should be huge, which can avoid the effects of snow bridging, where snow could sort of build a bridge over your sensor and not actually be measured. And also to reduce edge effects from the thermal discontinuity between your scales and the ground. If you have a much bigger area, your edge effect is less significant compared to the area that you're measuring in. But our sensor design is so very different that I thought it was worth trying something a bit smaller as well. Remember, our sensors were just built of thin layers of rubber, and the whole thickness of a sensor is just 30 millimeters. So the thermal discontinuity with the surrounding ground is actually pretty small. It's only 30 millimeters of rubber, so it's not going to make a huge difference thermally, which means those edge effects and the likelihood of bridging is much, much smaller. So I constructed some sensors that were 6 meters long, but only 24 centimeters wide. Very, very different from the huge 5 meter by 5 meter scale platform. It's a really long, thin strip, and we can chain lots of them together. So we went up and installed some of these thin strip sensors just to see what happens. And it turns out we got similar results from the thin strip sensor as the snow built up as we did from the larger scale mats, more comparable to the scales. And perhaps landowners who own the hydropower catchment areas would prefer a form factor like this. Instead of carpeting the land with all of these rubber mats, perhaps these thin strip sensors would be easier for them to work with and more acceptable to them as a solution. It certainly could be easier to carry, for example, and lighter to bring up into the mountains and install. So, as well as big areas, we sort of challenged that idea that bigger is better and went for a thin strip option that worked just as well. Oh, sorry, my PC just froze a bit there. There we go. So over the whole winter last year, here we have a graph that shows sort of the entire winter from November 2023 to May 2024. And the grey plot here that's most prominent early on and kind of comes ahead of the rest is the snow scales. And the different colours, the blues, the purples, the oranges, they were from different messenger sensors that we put out to test. And overall, it's promising that several of the different sensors all gave similar results. This is good that they are all in agreement. It's very promising that they match up, certainly in the snow melting phase, which is arguably quite one of the most critical periods for hydropower, because that's when we have the water coming out of the snowpack and melting away. So that's when we need to know. So we can be very, very happy with that. But we do know we need to fix this problem with the time delay, the non-linearity of the sensor response, and these settling effects as the snow builds up in layers. So I suppose that brings me to this year, really, which is where I'll be wrapping up this introduction to the Messenger product. Here is this year's version of the sensor, which now has some plastic tiles included on the top layer of the rubber, and this should hopefully even out the response. It should reduce the non-linearity that we see and reduce the dependence of the sensor on that kind of rubber deformation that can take time. We've also included different types of fibre inside the sensor. So different optical fibers have different sensitivities to the optical bending loss as they're compressed by the snow from above. And we have 3 different types of optical fiber now out in our different sensors. And this photograph shows this year's sensors installed at up at Myrkdalen. We have different sizes, different form factors, and all of them in similar locations to the scales, some of them on top of the scales again. So the very latest data, which I promised I would do when I said I'd give this talk, here is a photograph from yesterday. It's from our camera up in Myrkdalen. I didn't go. And the snow is actually not very deep so far. So maybe I should have given this talk in a couple of months. I don't know. But so far, especially on the scales, there's not very much snow coverage. So we can't draw any enormous conclusions so far. But here is the kind of the latest data. I think this is data up until the weekend. And even though we have just a few centimeters of snow registered by the scales, it seems reasonable looking at our photograph. We have just a few centimeters of snow water equivalent. We can see that our sensors are recording that reasonably well. There's good agreement between our sensors and the snow scale responses. So far, early days for this winter, but so far we think our improvements to the messenger system have paid off. So, in conclusion, I guess for the messenger snow water equivalent measurement project, we've used optical fiber sensing mats to measure snow water equivalent, and we could scale these to large areas. We don't need to have groundwork to install them, and we can have a sort of thin strip form factor rather than the bigger is better attitude that's been prevalent in the field so far. And we can say that our results correlate well with existing snow scales, the sort of existing state of the art. We're very pleased, and we've made some improvements this year for a field trial, which should make things even better still. So the Messenger SWE project is funded by Research Council of Norway. So we thank them for the funding. We thank NVE, who have been facilitating Messenger field trials. They've been really, really great at giving us their time and their expertise to talk over our ideas, but also giving us access to their measurement sites at Myrkdalen and Filefjell to test out our ideas. So we're very pleased with that. But we are interested in any other inputs you have from industrial partners, from university partners, in further field trials you might like to see. We have this winter, and we have funding for some field trials this coming winter as well. That will be the last winter of the project as it stands, is to perform some final field trials. But any insights into why we're seeing these snow effects? We are optical experts here and measurement experts. We're not necessarily snow experts. We've learned an awful lot, and we'd love to know more and get more insight into snow and what's happening in these sensors. So any contacts you have there would be great. Or if you're just interested in novel optical technologies for measuring things out in the wild like this, do get in touch with me or my colleague Peter. He's here in the call in the meeting today as well. Peter's the project lead for this project. But between us, we work on optical measurement technologies for all sorts of purposes. But yeah, that was the Messenger Snow Water Equivalent project. Thank you very much.